Hi everyone, my name is Emily Heffernan, and today I'm going to be presenting some work that I did with Mike Mack at the University of Toronto. So category learning is an important skill that we use to make sense of the world around us. For example, when I'm out for my daily working from home walk, if I see a flying winged creature in the sky, I'm probably going to guess that it's a bird. And based on this assumption, I can make inferences about this creature's other qualities. For example, it likely lays eggs and has feathers. But if this creature were a bat, then those assumptions would be wrong, because a bat's a mammal, so it doesn't lay eggs, and it has fur, not feathers. And many natural categories follow this rule plus exception structure, where most items follow a general rule, but some items, called exceptions, violate this rule. And in rule plus exception learning, the learner has to both detect general patterns across multiple episodes, while also detecting and remembering exceptions. And many brain regions have been implicated in rule plus exception learning, and one of these brain regions is the hippocampus. So existing work has shown that the hippocampus supports category learning. For example, in some work by Davis and colleagues in 2012, they found that hippocampal activation matches learning variables predicted by a cognitive model of category learning. Specifically, the more an item matched prior experience, the more the hippocampus was engaged. Similarly, hippocampal engagement corresponded to prediction error on a given trial. And importantly, for both of these variables, the hippocampus showed distinct signatures for items that followed category rules and items that violated category rules. And hippocampus is well suited to exception learning, in part because of its ability to rapidly form conjunctive representations that bind together multiple features. However, recent work has also shown that the hippocampus can rapidly learn statistical regularities and generalizations. And the hippocampus has two pathways that support these seemingly divergent cognitive skills: the trisynaptic pathway, or TSP, and the monosynaptic pathway, or MSP. And the subfields along these pathways give them their specialized properties. So the monosynaptic pathway runs directly from entorhinal cortex to CA1. And CA1 is characterized by dense overlapping representations. And these representations are well suited to forming generalizations based on existing knowledge. The trisynaptic pathway runs from entorhinal cortex through dentate gyrus to CA3 and then to CA1. And dentate gyrus and CA3 have sparse non-overlapping representations that are good for encoding distinct episodes. Now, the interplay between the monosynaptic and trisynaptic pathway means that sequence matters in hippocampal learning. So what the learner has previously experienced will impact how the hippocampus encodes the current experience. And we also know that sequence matters in category learning. So in a rule plus exception task, to enhance performance, CA1 should capitalize on early experiences to learn rules. And then mismatch signaling should then drive CA3 and dentate gyrus to create distinct representations of exceptions. So in this work, we wanted to explore this mechanism. So specifically, we explored how delaying the introduction of exceptions improves rule plus exception category learning. And we predicted that if the introduction of exceptions were delayed, the learner would be better able to learn general rules of a category structure. When they were later introduced to exceptions, they would be better able to identify and categorize them correctly compared to a condition where exceptions were introduced at the beginning of learning. So in other words, if you learn the rule first, you'll be better able to then learn exceptions. And we explored this concept using a behavioral category learning task. And then, to explore how this manipulation targeted hippocampal learning, we simulated the task using a neural network model of the hippocampus. And I'll start by describing the behavioral task. So in our task, participants learned to categorize images of flowers that varied across 3 diagnostic and 1 non-diagnostic dimension. And these stimuli were sorted into 2 categories using the type 3 problem structure defined in Shepard, Hofland, and Jenkins' 1961 paper. In this structure, each category has a prototype, and prototypes are maximally dissimilar, so they vary across all 3 diagnostic dimensions. Rule followers vary from their category prototype across 1 dimension, and exceptions vary from their category prototype across 2 dimensions. So they're actually more similar to the prototype of the opposite category. In our task, participants completed 3 learning blocks where they had to guess whether a flower preferred sun or shade, and they received full feedback after each trial. We randomly sorted participants into 2 conditions. In the early condition, participants were exposed to exceptions right from learning block 1, whereas in the delayed condition, we didn't introduce them to exceptions until learning block 2. And both conditions concluded with a test block that had no feedback and an equal number of prototypes, rule followers, and exceptions. And this design allowed us to test our key question, whether learning the rule well first, as in the delayed sequence, would better support later learning the exceptions. So to analyze our data, we used a general linear mixed effects model to predict accuracy using condition, type, and repetition as fixed effects, and participant as a random effect. So here we can see the categorization accuracy across different learning blocks. So the accuracy for prototypes, shown in purple, was quite high across both conditions, and the accuracy for rule followers, shown in pink, was slightly lower but still well above chance. However, the most interesting effect is the exception learning. So although the early condition shows poor chance level performance for the exceptions, which are shown in orange, in the delayed sequence we see a rapid increase in accuracy. And this pattern was also reflected in the test block. We also looked at how the exceptions from each category, which I'll refer to as exception A and exception B, were impacted. And we actually found that the effect that we saw was driven by exception B and not by exception A. And this difference is likely driven by a subtle but seemingly important difference between these exceptions. So our category structure was such that exception A was actually more similar to its category members than exception B. In other words, exception B was more exceptional. And this difference is actually reflected in the learning behavior. Okay, so we see empirical evidence that the learning sequence matters when learning rule plus exceptions categories. And it seems that learning the rule first does support exception learning. So we hypothesize that such a benefit to learning could be driven by how the hippocampus generalizes across and distinctly encodes episodes. And to test this hypothesis, we conducted simulations using an existing neural network model of the hippocampus and its subfields. We used a model made available in Shapiro and colleagues' 2017 work. And with this model, we did no hyperparameter tuning, we just used the out-of-the-box version of the model. So in this model, hidden layers represent hippocampal subfields, and the flow between these layers mimics the monosynaptic and trisynaptic pathway. The model accepts input patterns in the form of arrays in its input layer entorhinal cortex in, and then it acts as an encoder to try to replicate its input pattern in its output layer by adjusting the weights between hidden layers using error-driven and Hebbian learning that mimics hippocampal theta oscillation. So we adapted our behavioral task by transforming our flower stimuli into arrays. In these arrays, pairs of units corresponded to each of the stimulus dimensions, and the final 2 units were the category label. So we presented 2 learning sequences to the model that matched the early and the delayed condition, and we ran 500 simulations of each of these conditions. And then at test, we presented each of the stimuli to the model and recorded the settled activation in the output layer. To evaluate the model's categorization accuracy, we looked at how the output category label matched the target category label using Luce's choice axiom. And again, we analyzed our results using a general linear mixed effects model, this time with type and condition as fixed effects and simulation number as a random effect. And we are interested in whether the hippocampus, as defined in this model, would naturally predict the learning benefit for exceptions that we expected from the delayed sequence. And we found that it did, so we were able to replicate our behavioral results. Now, in our behavioral results, we also found this asymmetry in the effect for exception A and exception B. And the model was also able to capture this difference. So having replicated our behavioral findings, we next look at how our manipulation would affect the model's neural representations. So we used representational similarity analysis to interrogate the impact of our manipulation on representation. At test, we recorded the settled activation of the model's hidden layers corresponding to dentate gyrus, CA1, and CA3. And then we calculated the Pearson correlation between activations for each of the stimuli in each layer and in each condition. So in these plots, a darker color indicates more similarity between 2 items. And you can see by the darker color of CA1 that items in this subfield had higher overall similarity. And in all subfields and in all conditions, we also saw evidence of high within category similarity and lower between category similarity. So an item is more similar to items in its own category and less similar to items in another category. However, in these plots, it's hard to see the difference between the early and the delayed condition. So to make these differences more apparent, we next calculated the difference between the early and delayed RSA matrices. And in these plots, blue means that two items are more similar in the late condition, and red indicates that they're more similar in the early condition. So in CA1, we saw higher between category similarity in the early condition. So items in the opposite categories were less distinct from each other. Exception B had higher within category similarity in the delayed condition, as indicated by the blue in area 4 on this plot. So it was more similar to its own category members in the delayed condition. Conversely, exception B was more similar to its own category members in the early condition, as shown by the red color in zone 2. However, in these plots, it's difficult to see what's happening over time. So we next looked at the representational similarity at different time points throughout the experiment in a lower dimensional space. So we first used salmon mapping to project the representational similarity derived for each subfield and condition into a two-dimensional space at different time points throughout learning. We used a Procestes transformation to align these salmon mappings from different time points to the end of learning representation in each subfield. And in the mappings that I'm going to show, point opacity increases with time, and in the early condition, you can see that items are fairly well aligned, suggesting consistent encoding of category structure within each subfield across time. Items in category A, represented as circles here, are clustered to the left in each plot, and items in category B, represented as squares, are clustered on the right. And in the early condition, the exception items, which are shown in orange, are located closer to the center of each plot, so in other words, closer to the category boundary. But in the delayed condition, we see the exception B, which you can see with the red arrow there, shifts considerably towards its own category members. And we didn't see this effect for exception A. So overall, we see that in this model of hippocampal learning, having more experience with the category rule allows for exceptions to be better integrated into category knowledge. So to return to our original aim, we found that delaying the introduction of exceptions improves categorization performance in a rule plus exception task. And existing work has indicated that learning sequence can impact performance in rule plus exception learning, but our work is the first to manipulate learning sequence to specifically target exception items. And our behavioral learning results were also replicated in these computational simulations without us having to alter the model or conduct any hyperparameter tuning. And our model simulations demonstrate that the learning sequence effects we observed in our task naturally seem to fall out of hippocampal encoding functions. Now, one interesting finding in our study was this difference that we saw between exception A and exception B. We think this difference might have occurred because of differences in the non-diagnostic dimension. So specifically, when you consider the non-diagnostic dimension when comparing exception A and exception B to their category rule followers, exception B is less similar to its category than exception A, which would have afforded it a greater advantage in a sequence designed to emphasize exceptions. So it seems that in both human and model, the exception's overall similarity to previously encountered exemplars impacted memory, even when that similarity was due to a non-diagnostic dimension. And another interesting question raised by these results is the role that attentional tuning plays in rule plus exception learning. Many existing models of category learning have built-in attentional mechanisms that are crucial to their success. And the fact that our model that lacks an explicit attentional mechanism still did well suggests that dimension-wide tuning might be unnecessary or replaced by hippocampal encoding functions in certain learning contexts. So overall, we showed that manipulating learning sequence can influence performance in a rule plus exception task, and we presented novel computational evidence of hippocampus's sensitivity to such a manipulation. And these experiments serve as a starting point for future work on the role of hippocampus and its pathways in category learning and in cognition more broadly. And that concludes my talk. I'd like to thank Meg Schlichting and Catherine Duncan for their valuable guidance and feedback as I completed this work. Thank you to all members of MacLab and especially to Carly and Sophia for your help on this project. And finally, thank you to the funding agencies that made this work possible.